Alright, these are the 4 notes on logarithmic functions. And what we're going to do is kind of reintroduce you guys to the concept of logs. You would have talked about this to some extent in Algebra 2. The reason we did the 4-1-4-2 day set of notes was to lay the groundwork for logarithmic, which that groundwork is exponential, and the connection between these two is they're inverses of each other. So it's good to start the discussion with maybe a graphical approach, to sort of look at the two graphs and talk about some of the comparison pieces of the graphs. And then go back to the idea of how you find an inverse, which we talked about in Chapter 2, and then build that into where the log comes into play. So let's start out with the graph itself. The blue being your exponential graph, which we already talked about. Think about coordinates that I would choose, x values that I would choose that make this graph easy to draw would be an exponent of 0, because anything to the 0 power is 1. Then maybe to the first, depending on what your base is. Again, keeps it easy to draw. Your graph looks like the blue, and then the blue asymptote. I'm going to slide that into place so we can look at that idea. And, again, why was there nothing down here? Well, if you take your base and you raise it to a positive exponent or a negative exponent, you never produce a negative y value, and you never produce 0. So the reason no graph sits down here for an exponential unless you reflected it, but otherwise, outside of that, is because you can't go, for example, 2 to what exponent, positive or negative, produces 0 or a negative number, and those are impossible questions to answer, things that happen. Now on the flip side of that, look at your log. So if we got an x-intercept with this coordinate of a y-intercept with this coordinate of 0, 1, then it becomes an x-intercept in a log 1, 0. And there's the inverse idea in a nutshell, right? I can just switch the x, y parts of the coordinate and replot. That's how we draw inverses from the past. So if we had a horizontal asymptote with an exponential, now we have a vertical asymptote. That would be an inverse switching x, y idea again. What we'll get to understand here in a little bit when we start talking about graphing is why is there no graph over here, and why does this graph sit entirely on the right side of the asymptote unless I reflected it over the y-axis. But outside of that, why is there nothing here? And there's reasons we'll get into in a minute that are counterpart reasons to why we can't have exponential graphs sitting down here. We'll come back to that in a little bit. Now let's just kind of switch over for a second to the idea of finding the inverse, so an algebra process. If you guys remember that process, you would start with the original equation, you would switch x and y in the equation, and then you'd solve for y. This solving prior to now would just been an algebra kind of process that would get us there. We'd do whatever we need to manipulate, get a y equals equation, whatever that was, it would be our inverse. In this instance, when you switch x and y and you go solve for y, how do you do it when y sits up here? And basically what we can do is we can log both sides. And by logging both sides or introducing a log into the equation, we can get that exponent down. That's a concept we'll talk about a little bit later in the chapter, but it at least allows us to talk about where does the log come from. It comes from the exponential inverse idea, and then log becomes an operation. Again, we'll hit those details with a little bit further down the road. Now, just to kind of get back into the design of the equation, it goes log-based number equals exponent. That's the way you want to say it. That's the way you want to talk yourself through it, especially when we start doing conversion, turning log into an exponential and vice versa. So we want to keep track of where's the base, where's the exponent, where's the number. So log-based number equals whatever. Okay, let's just do a little bit of quick conversion. I think that's a good way to get you guys going. So in every logarithmic equation sits an exponential, and I think if you think about it as a what to the what equals what, an exponential question, you can look at this, and I think everybody can pull it out of there pretty quick, and keep in mind what's the base here, but 2 to the 4th is equal to 16. So what we're really trying to do here is identify like corresponding parts, I guess, in different styles of equations, logarithmic and exponential. If you guys look at the second one, you can see base 27 to the 1/3 is equal to 3. All you're really doing is producing true exponential statements from a logarithmic, so a rewrite. And then go in the other direction, 2 to the 5th equals 32, so log base 2 of 32 is 5. One of the things we want you guys to do actually fairly quickly, even today, like within this lesson, and definitely as we move on through the chapter, is we'll get rid of this part of the problem, like this won't be here. And we'll just say, what is log base 2 of 32? And even that can become a smaller part of a bigger problem, and you should be able to just look at it and go, yeah, it's 5. The answer is 5. Okay. And what we want you to be able to do pretty quickly, like within the first day or two of this, is to not have to do conversions, but just like I look at this and I know exactly what's going on. I don't think really anything about exponentially. I don't do any conversion, I just know the answer. We'll get there. Okay, so then the last one here, log base 4 of 1/16 is 32 because 4 to the negative 2 is 1/16. So conversion's fairly easy, I think, once you get the idea of what parts correspond. It's just a rewrite. But the rewrite has importance for us in a couple different areas when we do word problems and when we do solving equations. There is a fair amount of rewriting that goes on. Even when we find inverses, you'll see that too a little bit later. So if we're going to talk about log, we got to talk about ln. So base e in this case. So we did that with the 4142 notes. Here's your base e graph. Natural exponential. And then its counterpart is the natural log. So ln is the symbol for that. When you see anything ln, just think log base e. This will never be written anywhere. So if you're like looking through an assignment or a test or quiz or whatever, you'll never see log base e. It's automatically ln, but this is definitely what's going on. I think it's a great way to think about the first day. And then you just get used to it, and you'll just, anytime you see an ln, you'll immediately think base e. All the same ideas, inverse-wise, are here, so I'm not going to recap asymptotes and coordinates, but just to show you that these two graphs are inverse of each other. So base e, natural log. And then a little bit of conversion. Again, when you read ln of 4, at least today anyway, think of it as log base e of 4, which I think makes the rewrite go a little bit smoother the first time anyway, because you're searching through this going, where's the base? Well, base e. So e to the x equals 4. And then again, when I see an e, it helps you at least the first day to go, well, that's actually log base e of 3, equals x, but of course you'd want to write it as the ln, natural log. So this idea is, I think first day is fine. It helps you understand what ln means, but then try to drop that off as quick as you can and just go to natural log. Okay, a quick side discussion on properties just for a second. So we're going to run through at least the first three as a well, they're true because what? Because of what's true exponentially. So when you look at any log equation, it's a property. And we say, well, why is this true? What are the reasons for this being true? Just think about why it would be true exponentially. You've answered the question. These first two especially are just log versions of rules of exponents that you all know. If I do the rewrite, for example, on the first one, it says a to the 0 is equal to 1. Well, anything to the 0 power is equal to 1, and we all know that. This is just the log version of that same rule. How this reads is slightly different. It says if you log any base of 1, that is equal to 0. But it is the log version of anything to the 0 power is equal to 1. And then if I'm doing ln and think of it as log base e, then this would be e to the 0 is 1. So if you ln 1, or you log base e of 1, or you log any base of 1, you get 0. The rewrite on this one would read a to the first equals a. So number 2 is actually the logarithmic version of anything to the first power is itself. Which again, we know this, like obviously this is true, we all know this one. And then if I'm thinking log base e, then e to the first is e. So log of any base of the same number is equal to 1 is the way I would translate that. The third one that I have circled in red, and the reason I circled it is because this is kind of our workhorse property. It does a lot for us in all different ways of dealing with logs. When you do the rewrite, it doesn't fit into like sort of a, like a universal rule that we all just know, but it's definitely common sense. If you rewrite it, it reads a to the x equals a to the x. Well, of course that's true. It's just basically it's a true statement. So being that this is true, this would be true. And then if we do log base e, again, same idea. The last two are not log properties. Sorry, well, the fifth one is, the fourth one is actually exponential. But it is useful now and then. It kind of pops up. I put memorize above it because it's not as kind of obvious, I think, as the first three that sort of fit into like, yeah, no kidding, right? But if you do a rewrite of these, you can at least see why they're true. So if I rewrite this logarithmic, because it's exponential right now, it would read log base a of x equals exponent. Okay, well again, what you produce would be like an obviously true statement. So this side here is actually log this base raised to this exponent equals, again, a true statement. Right? So if you look at this, it's like, well, clearly that's true, so now I can say this is true. And then we can do the same thing with an ln or a log base e idea. So it's one to know. Like I said, it pops up here and there just to keep that in the back of your head as, when you need it, maybe you have it memorized. You'll use it once in a while. The last one we're going to, again, is just kind of a nice property for solving, actually. And I'm going to tell you guys what it equals. So here's what we get. If you have log of the same base of two different expressions, you can drop the logs and set the expressions equal, which is a useful solving tool. I want to see how it is that it works. If I do the rewrite, and this is kind of funky, but so I'm going to go this side as my base. Base a, so a to the exponent equals numbers. So base to the exponent equals numbers, what you see here. And then I apply number 4 to it and say, well, that thing actually is equal to y, then y is equal to x. Now, not you got to have this whole thought process memorized, but it's just saying like here's how it is that it works. But again, a useful tool when we're solving. And we'll get to that a couple sections down the road. Okay, let's get off the properties and just get to using them, right? Get into it and see what we can do with it. So this is a slide where we take off equals and you fill it in yourself. And some of them are going to be kind of easy up front. Like when I look at this one and I'm applying this property and maybe not trying to do any kind of conversion or exponential thought, but just like, hey, here we go, right? Well, clearly if that's the case, the answer is 4. If you want to say y, you can go, well, because 5 to the 4th is 5 to the 4th, if you do like an exponential rewrite. Log base of the same number is a 1, that's a property, but you can still use this as a way to think about it. And when the number, the base, and this number are the same, then I think this property stands out as, like obviously, but here they're not, but then it's going to be a kind of a redesign a little bit. So what you want to do is shoot for making this base 4, which I think you guys will get that pretty quick. So log base 4 or 4 to the 3rd. And what I'm really doing is taking 64 and making it a base 4 expression. And as soon as I do that, then I'm right back to that property. So I can say that's 3. When you're doing something like this, trying to do the equivalent idea, if you look at, ask yourself the question, can I make 8 a base 4 and have a whole number exponent? Like 8, so 4 to the what is 8? And if I say I can't answer that with a whole number exponent, then that should drive you to, hey, it's a fractional exponent. So I got to think of that, how I would do that. But you guys have done fractional exponents. We did them in the review chapter. You guys should be able to pull that back in. So the way this would work is the square root of 4 is 2, 2 to the 3rd is 8, or 4 to the 3 halves is 8. And then as soon as I pull that off, then I'm good to go with the property. So like I said earlier, the workhorse, right? It kind of throughout, I can see this going on in every spot that I'm at. Get to know this one really well. So in the process here, with a little bit of rewrite, what I'm going to do is take the square root off for a second. We're going to change 3 into base 9, and the way you're going to pull that off is by thinking of 3 as being 9 to the 1/2. So what I want to do to get this property going as often as I can is create the base and this number being the same, which means this number has to be rewritten as to match. So 9 to the 1/2, the square root of 9 is 3, and then what I'm going to do is tack that root back on, because that's another exponent of 1/2, and then what I have is 1/4. Because this would be log base 9 of 9 to the 1/4 is 1/4, and again I've managed to pull this property off. Okay, so we've seen that one in action quite a bit. Do a little ln here quick. So a little bit of rewriting. There's the idea of 1 over e is e to the negative 1 if you want to think about it as log base e, but again try to kind of get over that, just apply the property. These two are the same property. Right? If I wrote log base e of e to the x equals x, put an e here and here, but we don't do that, we say ln. So the ln of e to an exponent is its exponent, so the answer to this one is negative 1. And then here's me using that rule again, just kind of when I sort of got to memorize a little bit, but the answer to that one is pi. Okay, so there's, trying to be able to use the properties. No real work on paper, this is kind of all in your head sort of stuff. And it's the idea of creating this situation as often as you can to help manipulate or make the problem easier to work with. So we're going to switch over to solving for a sec, and then I'm going to stop this video and we'll pick up with another one. But the idea here is do a bunch of rewrites and answer the question. What we want you to do ideally, this section I'm going to pop up here is the rewrite section. We want to be able to cross that section off and just go to an answer. But I think today, useful to do the rewrite. So I'm going to pop them up quick. So here's all of these rewritten in their exponential format. And once you're here, just answer the question. Right? So we know that's going to be 16. We know that's 10. 4, I'm going to think about that one for a second. 4 to the 5 halves is 32. And then what we'd like you guys to be able to do, again, is to try to go skip over this step, especially on paper, and go to answer. But I think, again, today, if you feel like I still like this, I want to do this, go right ahead. All right, I'm going to stop this video here. The last couple concepts will be a shorter video, but this is a good breaking spot, so I'll pick up with part 2 in a second here.